Welcome back to the deep dive. Today we're digging in something really quite fascinating in AI. Can large language models, LLMs, effectively act like their own internal Google?
Hmm.
We're looking at a cutting-edge idea called self-search reinforcement learning, or SSRL. It's not just about answering questions.
No, not all.
It's about these models becoming sort of autonomous knowledge explorers, digging through their own vast internal data stores to find answers,
Yeah.
all without constantly pinging external search engines.
Right.
So our mission today is to uncover these, well, often hidden search skills within LLMs and see how SSRL boosts them based on this really interesting paper by Fan and colleagues.
That's right. And the big challenge this paper really tackles is the cost. Training LLMs for these agentic search tasks where the model acts like a researcher,
Making decisions, searching.
Exactly. Querying, sifting information, trying different paths. It traditionally needs constant and expensive calls to external search engines.
Yeah, I can imagine.
But what the researchers found, and this might surprise you, is that these LLMs already have a massive amount of world knowledge just baked in from their training data.
From all that web text they ingest.
Precisely. So this core idea of self-search, where the LLM simulates the whole search process internally, it builds right on that existing knowledge.
Right.
And SSRL, that enhances this internal search using reinforcement learning. The key takeaways are pretty striking.
Lay them on us.
LLMs genuinely hold a lot of internal knowledge. SSRL significantly improves their performance and cuts down on hallucination, making stuff up.
Always good thing.
And maybe the most exciting part is the smooth sim-to-real transfer. Models trained to search internally can then apply those skills effectively in real external search situations.
Okay, let's unpack self-search a bit more. It sounds a little sci-fi. How did they actually, measure this internal capability?
Well, they found a pretty clever way. They basically prompted the LLMs to simulate the entire search process internally.
All inside the model.
All inside. So the LLM generates its own queries, then it retrieves the information using only its own parameters, its stored knowledge.
Like thinking to itself.
Kind of like an internal chain of thought, yeah. The model auto-regressively generates the whole reasoning path, the thoughts, the simulated searches, the info it finds, the answer, all in one sequence.
Wow, okay. And how do you score that?
They use a metric called pass at K. It's pretty straightforward. If you let the LLM generate K, different possible search paths or answers.
Give it multiple tries internally.
Right. If any one of those K tries gets the right answer, it counts as a pass.
Got it. So more tries, potentially better results.
And that's exactly what they saw with this inference time scaling. LLMs showed really strong scaling behavior. As you increase that inference budget, the number of samples, K,
The performance goes up.
significantly. Take the Bamboogle benchmark, which is pretty tough. Llama 3.1 8B instruct hit 87.2% accuracy with 1,024 samples.
Okay, 1,024 internal attempts.
Yeah. And that was a 150% improvement over just letting it have one shot, pass at one. It really shows how much knowledge is in there if you can just, encourage the model to find it.
A huge leap.
And even on BrowseComp, which is notoriously hard and usually needs web browsing, models like Qwen 2.514b and Llama 3.18b actually beat a baseline model, which only scored 10% once they had enough internal samples.
Without external tools at all.
Without external tools in that specific test, it really highlights this internal potential.
That is surprising. Now, you mentioned Llama and Qwen models. We often hear about different model families being better at certain things, like coding or math. Did they see differences here?
They did, and it's a really crucial point. They found that the Llama models actually performed better than the Qwen models specifically in this self-search context, leveraging their world knowledge priors.
Huh. But Qwen is often great at reasoning tasks, right?
That's the interesting part. Qwen often excels in math or code, but here, for internal world knowledge search, Llama had the edge. It suggests that this self-search ability might be somewhat distinct from, say, complex reasoning priors.
So a model could be great at math, but not necessarily the best internal fact checker. It's like a different kind of intelligence.
It seems that way, yes. A distinct capability.
Okay, that's a big insight. And you touched on efficiency earlier. Can smaller models actually compete with the behemoths using this self-search sampling?
Absolutely. That was another really compelling finding. Smaller models could reach performance comparable to models nearly 10 times larger just by using repeated sampling effectively.
Seriously, like an 8 billion parameter model matching a 70 billion.
On Trivia QA, yes. With 124 samples, Llama 3.1-8B instruct scored 81.2%. The much larger Llama 3.170B instruct 81.4%.
That's basically identical.
Practically. It really emphasizes efficiently using the knowledge you have rather than just raw size.
So it's not just about having the biggest brain, but knowing how to access the information within it. Like a well-organized library versus a massive, messy one.
A good analogy, yes.
This kind of challenges that idea that just making the model think more, give it more reasoning steps, is always the answer. Did the paper look into that? Like, does more internal thinking always help in self-search?
It did, and the further analysis section had some counterintuitive results there. For Qwen3 models in these self-search settings, just increasing the thinking tokens, the length of that internal monologue didn't consistently improve performance.
So more thinking wasn't better?
Not necessarily. Solving these agentic search tasks seems to lean more on efficient knowledge utilization than just long chains of reasoning. Shorter chains of thought, shortcode, seemed preferable for token efficiency here.
Interesting.
And other techniques they tried, like multi-turn self-search, letting it iterate internally multiple times, or self-search with reflection, where you prompt it to reconsider.
Like, hold on, check that again.
Something like that, yeah. Phrases like, wait. Those actually hurt performance compared to just simple repeated sampling, especially when you factored in the token budget.
So keep it focused on efficiently grabbing the knowledge.
It seems so. Efficient knowledge utilization is key for this internal search. And even though pass@k showed the knowledge was in there, actually picking the single best answer using methods like majority voting only gave marginal gains.
So finding the knowledge is one thing, reliably extracting the right piece is another challenge.
Precisely. It highlights that extraction problem.
Okay, this internal capability is clearly powerful, but maybe a bit tricky to harness perfectly. So how do we make LLMs better at it? How does SSRL actually enhance this?
Right. This is where SSRL comes in. It uses reinforcement learning specifically to help LLMs get better at, as the paper puts it, exporting world knowledge from their own parameters.
Okay, using RL. What's unique about SSRL's approach?
The really crucial difference is that the policy model, the part guiding the LLM's actions, acts as both the reasoner and the internal search engine.
It does both jobs.
Yes. It retrieves knowledge from its own parameters. This simplifies the whole RL objective quite a bit, makes the training more direct.
Clever.
Yeah.
And how do they actually train this? What techniques did they use?
Well, one really ingenious part was information token masking. During training, they would actually hide the content within the information tags.
Even though the model generated that information itself.
Exactly. And surprisingly, hiding that self-generated info still boosted performance.
Why would that be?
It seems to force the model to engage more deeply with the reasoning process, how to get the information, rather than just, copying the answer it just found. It builds a more robust problem-solving skill.
Makes sense. And they use rewards, obviously, being RL.
Right. A two-part reward system. First, an outcome reward, simple, +1 for correct, -1 for incorrect.
Standard stuff.
But second, and this is important, a format reward. This nudges the model to stick to that structured output using the think, search, information, answer tags correctly.
So it learns to show its work, basically.
In a structured way, yes. It ensures these well-organized reasoning paths. They weighted the outcome reward higher, of course, but the format reward keeps things disciplined.
A smart combo. So how well did it work? Did SSRL models actually outperform others?
The results were pretty clear. SSRL-trained models consistently outperform the baselines that use external search engines like Search R1 or Zero Search, and also models using simpler chain of thought.
So internal search, when trained right, can beat external search.
In these tests, yes. It shows LLMs really can be effective reasoners and internal knowledge retrievers simultaneously.
Any difference between base models and instruction-tuned ones?
Yes, interesting distinction there. Instruction-tuned models like Llama 3.2 3B Instruct were generally significantly better when using internal knowledge.
Okay.
But the base models actually did better when external info is provided. It suggests maybe different optimizations are at play depending on whether you prioritize internal recall or external tool use.
Fascinating trade-off. What about training efficiency? RL can be notoriously complex and time-consuming.
SSRL showed substantially improved training efficiency. They reported a 5.53x reduction in training time compared to Zero Search.
Wow. Over 5 times faster.
And crucially, it maintained steady reward growth without collapse, suggesting it's a robust and stable training method. Very cost-effective.
That's a huge practical advantage. But the big question for any AI like this is the real world. Can these internally trained models actually use real search engines effectively? That sim-to-real transfer you mentioned.
Right, and this is a major success reported in the paper. Syn-to-real generalization seems to work very well. SSRL models can seamlessly integrate real search capabilities.
Wow.
You simply replace the internally generated information content with actual results from, say, Google search. The model uses the same format it learned internally.
Smooth transition.
Yeah.
And does performance improve with real search?
Generally, yes. Performance consistently improves with more turns of real search. And importantly, SSRL models in these sim-to-real settings often hit top performance with less actual online searching than the baseline models needed.
More efficient even when using external tools.
Exactly. And they even tested an entropy-guided search strategy.
Entropy, like uncertainty.
Yeah. The model only triggers an external search when its own internal uncertainty, its entropy, goes up.
Only search when you're not sure internally.
Right. And this approach cut the search frequency by 42% while keeping performance almost the same as searching all the time. Huge potential for cost savings.
That's really smart. Making the model discerning about when it needs outside help. Now, the paper also mentioned test time reinforcement learning, TTRL. What's that about?
Ah, yes, TTRL, another technique they explored. It basically allows for some learning or adaptation during the testing phase. It showed better performance than another method called GRPO.
Improving on the fly.
Sort of. Llama 3.23b instructs average performance improved by 59% with TTRL, and these models got substantially better on BrowseComp, even without external search.
Interesting. Any quirks with TTRL?
One interesting observation was with smaller models using TTRL on BrowseComp. They often preferred a different strategy. Point out an entity first and check if it meets all requirements, rather than a strict search-then-answer sequence.
Again, showing that rich internal knowledge and flexible strategies.
Exactly. But there's a potential downside noted. TTRL might create a bias where models over-rely on internal knowledge and struggle a bit to adapt easily to real external environments if they differ too much.
A balancing act then.
Always.
So let's pull this all together. What's the big picture here? It really feels like LLMs are more than just text generators. They're like these implicit world models with deep search capabilities hidden inside.
That's a great way to put it. And SSRL significantly unlocks and enhances those self-search abilities. It demonstrably outperforms methods relying solely on external APIs and, critically, allows for that robust sim-to-real transfer. Meaning, this paves the way for genuinely more autonomous and scalable LL agents. Agents that can function effectively without constantly needing external search, which means real cost savings and better efficiency.
So the final thought for you, our listeners. Consider the implications here. An AI that doesn't just reason, but can effectively search its own mind for information. External knowledge becomes a tool it can choose to use, not something it absolutely depends on for every complex query. What new possibilities does that open up for how we design, train, and interact with these increasingly self-sufficient AI systems?